Welcome back to another episode of Dave Does Math from Home. Today we are talking more about volumes of rotation. We started talking about volumes of rotation with section 6.3, and in that section there was pretty much only one technique we were using for all of these volumes of rotation, and that was that we were slicing our shape perpendicular to the axis of rotation. So when things were rotated around the x-axis, we would slice them vertically, so that our vertical little slices spun around the x-axis gave us disks. That was the only technique we talked about in section 6.3. This section we are doing the same thing. We're taking shapes, we're spinning them around axes or around lines or something, and we are getting the volume of the shape that's generated by that. And once we do that, we are, or not once we do that, the difference here is we're using a different technique. Instead of making all of our slices be perpendicular to the axis of rotation so that we get a nice little disc, now we're going to see what happens if we make slices that are parallel to the axis of rotation. See what that gives us. So bear with me here. We're going to start with an example so that we can talk about this as we go. I want to look at the function y equals x squared plus 1 on the interval from 0 to 3, which is this area. If I were going to spin this around the x-axis in a section 6.3 problem, I would make these little vertical slices. When I take this vertical slice and I spin it, I'll get a little disc. I know the volume of a disc. I can do that problem. That's a 6.3 problem. I'm not going to do that problem again. What I'm going to do is, I'm going to take the same vertical slice. I'm going to spin it around the y-axis this time. So when I spin this shape around the y-axis, I get the resulting three-dimensional shape you get. I like to think of it as like one of those, maybe I shouldn't be telling you this. I think of this shape as like the solid glass part of like a shot glass, where the glass itself has straight vertical edges, but there's like a round, it's like a round scoopy bit that's been cut out of the middle. So it still has a, it's a cylinder straight through, it's just got like a parabola carved out of the middle. That's the shape we're going to get when we spin this thing around the y-axis. My little shot glass shape. This is x equals 3. But before we start talking too much about that, we really need to talk about what shape we're going to get when we spin this little slice of area around. So when you spin a slice of area around like that, a vertical slice around a vertical axis of rotation, you get sort of like this hollow cylinder shape. I like to think of it, I think the best way for me to imagine this is like, if you imagine taking like a can of tuna, and you cut off the top and you cut off the bottom so that all you have is like the round sort of like shell of the can, with there's no top, there's no bottom, there's nothing in the middle. That amount of aluminum is going to be approximately this shape. Or like if you take a can of soup. If you take a can of soup, you cut the top off, you cut the bottom off, you just have this like tin can with no top, no bottom, just a hollow cylinder and an angry cat. Why are you so angry, cat? Yeah? Do you mind? Can you not? I said the word tuna. I'm not feeding you. Anyway, when you spin this shape around, you get this like, I like to think of it as a hollow, empty, no top, no bottom tin can. which is shockingly difficult to find the volume of if you're trying to think of how you can do that. Sort of like the this is Tsuna. She really wants to say hi. Say hi, Tsuna. Everyone see Tsuna? Tsuna is the Japanese word for tuna. And she's mad about it. Tsuna, I love you, but now's a really bad time. Go away. Alright, so we get this empty tuna can, soup can shape with just like the sides, the shell of it. And we're trying to find the volume of that. And like the most intuitive sort of like natural way you can go about that would be to try to use the volume of a cylinder. We can try to approach this problem like we approached the donuts from the last problem. The donuts were essentially like big cylinders with like smaller cylinders punched out of the middle to make this like washer shape or like a CD shape with a little, the actual little hole in it. That works in those cases because there's like a meaningful difference between the outside radius, the big radius, and the small radius. When you're looking at something like this, the thickness of this shape is purely this is just an illustrative tool I'm using to show you that there's a shape there. When we take the integral, we're going to shrink the width of that shape down to nothing. So trying to find the volume of one cylinder and then a separate cylinder when the difference between those cylinders is infinitesimally small, that's not going to work for us. The way that we are going to find the volume of this thing is, we're going to imagine this hollow cylinder something like this. This is a rolled up piece of paper I have, just a little notebook paper. If I roll it up, I can kind of pretend like this is more or less the shape I get when I spin this tiny, thin fragment of rectangle around in a circle. You spin it around in a circle, you get something like a really hollow little shell here. And then the problem becomes, I want to find the volume of this hollow little shell here that looks like a cylinder. But we know that using cylinder formulas is not going to work. So here's what we do instead. You let it unroll. The volume of this hasn't changed. I still have the exact same amount of paper. If you roll it up into a cylinder, you have a cylinder of paper. If you unroll it into a rectangle, you still have the exact same amount of paper. The volume of this has not changed at all. But the volume of this is very easy to find. Unrolled, this cylindrical shell thing, pipe thing, I tend to think of these most commonly as pipes. That's the word that I use the most when I'm referring to these. I think the book calls them shells, but every time I see the word shells, I think of like macaroni and cheese. So that obviously is not going to work. So I think of these shapes as little pipes. I think that's the best way to conceptualize what kind of shape you're dealing with, because you can pipe communicates to me that you definitely have a cylinder that is hollow on the inside. You're just looking at the walls of a cylinder. To me, it is the most illustrative word. So we have this pipe, and the volume of this pipe that we get is the same as the volume of this rectangle that we have if we unroll the pipe. And so the volume of a pipe, this is a rectangular prism, we're going to have 3 dimensions. Length times width times height. Or maybe instead of height we can use, no, we can use height, this is fine. So, we have to figure out which dimensions of this are which, of our unrolled pipe thing. And this is the challenge here. The height, maybe I don't want to use height here. No, we can use height, that's fine. One of the dimensions of this thing is going to be the height of your pipe. That's pretty much the easy one. So if we want to call this the height, then the height is always going to be, in this case, the height is always going to be this y value, which is x squared plus 1. That's my height. The length of this, from one corner to the other after it's unrolled, when you roll it up, or when you unroll it, and you're looking at this piece of paper, you want the length to be from here to here, this distance. So the way that we can get that from this is recognizing that that distance rolled up is the circumference of this pipe. So let's do h equals x squared plus 1. Length equals the circumference. Circumference is 2 pi r, and r is this distance here, between the shape I have and the axis itself. And that distance is just x. So I have x here, I have y here, which is x squared plus 1. That's 2 of the dimensions. The width is the last dimension I need, and the width of this is going to be the thickness of this sheet of paper. Or if you're still thinking about this as a tuna can, that would be the thickness of the tin can or the aluminum can you have. Or if it's a pipe, it's the thickness of the walls of your pipe. And that is the dimension that we are shrinking down infinitesimally small to basically nothing. And we call that tiny little sliver of the x-axis. In this case, we call that dx. So, the volume of my pipe is 2 pi x times x squared plus 1 times dx, which we can simplify into 2 pi. I'm going to distribute the x in here, so I have x cubed plus x dx. For any given x value in this interval, this will give me the volume of the pipe I get for spinning that particular x value around the y-axis at this height. So, as always, to get the volume of my entire shot glass shape, all I have to do is integrate the volume of this pipe. So I'll go from 0 to 3 because those are the x values I'm interested in. 2 pi can stay on the outside because it's a coefficient. I have to integrate x cubed plus x dx, and I will get x to the 4th over 4 plus x squared over 2 from 0 to 3, which is, I'm running out of room here. I think I can finish this on the bottom edge there. 2 pi, oh no, I got a better idea. I'm going to distribute the 2 in here to cancel half of that and all of that. So it's just going to be pi times 3 to the 4th is 81. 81 halves, because I still have a 2 at the bottom of that, plus 9 minus pi times 0 plus 0. 81 halves plus 9 is 18 halves. So this is 99 halves pi. There you go. That's the volume of your weird looking shot glass thing. 99 halves pi cubic units of volume in this. And in any case, I'm not super concerned about what the volume actually is. This problem is mostly just to illustrate the idea of the geometry of getting a pipe and finding its volume. So, that was the introduction. We have a couple more examples that we need to do, including, I promised promised that we would redo an example from the last video that went horribly awry. Promised it was easier this way. We need to verify that. So I'm not going to do it in this video. I'm already at 15 minutes. We're going to shut this one down. But stay tuned. There's another one coming right after this, and then we will do more examples.